So since we understood what is PageRank and how PageRank works, and since we have already understood one of the problems in PageRank, that it is not able to capture the diversity of a network, now we discuss something called DivRank. Okay, so diversified PageRank or whatever, diversified rank. So in case of PageRank, we already mentioned that top ranked nodes in a PageRank are often not diverse, right? And diversity is important. For example, say you are in a city and you want to explore different restaurants, for example, right? And you don't have any such preference, but you prefer that, I mean, whenever you search about a restaurant in the city, the top ranked restaurant should come, right? And what would be your expectation? Your expectation would be a best ranking system should be able to produce a rank where the top few restaurants would have diverse recipe. For example, one restaurant is famous for its chicken related items, right? Other restaurant is famous for its more of a continental type of items, right? Other restaurant is famous for its vegetable items, right? Mostly veg restaurant. So you expect that in the top 5-6 ranks, you should not have any redundancy, meaning that you should not be shown restaurants which are famous only for Chinese foods, for example, or only for continental foods, right? There should have a diversity in the top ranks, right? But what happens in case of PageRank is that PageRank always returns restaurants which are popular, right? Irrespective of whether they are diverse or not. Okay, so therefore diversity is important, and and diversity is important because we generally want to reduce the redundancy in the ranking process, right? So a good way to tackle this problem is that you make a trade-off between prestige and diversity. So prestige can be captured using PageRank. So can we come up with some sort of trade-off which gives equal weightage or equal importance to both prestige and diversity? So DivRank, diverse rank or diversified rank, is one of such solutions. Okay. So here is the graphical example that I briefly gave in the last lecture. So let's say this is the network. Okay. And in this network, if you run PageRank, what would happen? That node 2, node 3 and node 1, these 3 nodes will be returned as top 3 nodes. Okay. But you may not want to return all these 3 nodes, because all these 3 nodes basically represent this component of the network. Rather, what you basically want that some node from this component would also be returned, some node from this component would also be returned, and one node from this component can be returned. So this is exactly what DivRank does. DivRank would return node 1, node 4 and node 5. So this is DivRank's output, node 1, node 4 and node 5 as top 3 nodes. Here the size of the node corresponds to the prestige. So in case of PageRank, you see that these nodes are of equal size, right, followed by these nodes, whereas here you see that these nodes are top ranked nodes. Other nodes do not have any significant rank at all, right? So what DivRank does, DivRank kind of allows nodes to compete with each other. There is no collaboration, there is no cooperation. In case of PageRank, there is a cooperation, because ultimately prestige flows from one node to another node, and you basically you basically allow the node to collaborate with each other to increase each other importance. Here you basically allow the nodes to compete with each other. Okay. So if you look at this portion of the network, what happens is that due to the competition, a node which defeats other nodes, that particular node would keep on absorbing importance from the remaining neighbors of the node, and the importance or the prestige would basically go on and on, go on increasing over time. That's the idea. Okay. So now how do we implement this? How do we materialize this idea? So DivRank is based on something called Vertex-Reinforced random walk. What is Vertex-Reinforced random walk? Basically the idea is that whether you visit a particular restaurant or whether you visit a particular museum, right, depends on the number of times that restaurant or that museum have been visited in the past. So the more a node has been visited again and again, the more the prestige of the node would increase more and more over time. So the transition from node U to node V depends on node V's previous visits. How many times node V has been visited by the random walker? Okay, that's the crux of the theory here of DivRank. So here there is a notion of time heterogeneous random walk, right? Meaning that this jumping probability from U to V. So far, if you remember the PageRank algorithm, right, the transition probability from U to V, that remains same, and that is always uniform, right? Uniform in the sense like given a particular node, if there are 4 forward nodes, the probability of choosing one of these forward nodes is uniform. It doesn't depend on the distance, the other node, the other part of the node in the edge, right? Whereas in Vertex-Reinforced random walk, the idea is that the transition probability that keeps on changing over time. It's not static, and it is dependent on the number of times that you have visited the destination node or the end node of the edge. So if there is an edge from U to V, right, and this probability depends on time, right. So as the time progresses, what would happen is that this probability would change with respect to NTV. What is NTV? NTV, the number of visits of node V at time t, and this is dynamic. Since this is dynamic, this is also dynamic. You have some initial probability, initial transition probability, which is same as the PageRank kind of probability, but over time this would increase or whatever decrease depending on this, right. So this is called Vertex-Reinforced random walk. You are reinforcing based on the number of visits of the particular node. Okay, so let me first use my whiteboard and discuss some of the important components. So let's look at in case of traditional PageRank, right, time homogeneous random walk. Now why it is time homogeneous? Because the transition probability doesn't depend on the time. So in case of time homogeneous random walk, the probability of a node V or prestige of a node V, right, this is not probability, this is basically prestige or whatever, PageRank, whatever, right. This is what? This is essentially sum of P of UV times P of T U, if there is an edge from U to V, okay. So this is V, this is U, okay. So you have So sorry, this is t minus 1. So at t minus 1th time, t minus 1th iteration, node u has some prestige, and that is pt minus 1 u, right. Now that would basically move through this edge, which is this probability p of uv. Now p of uv in case of PageRank, p of u would be 1 by the number of forward edges of node u, right, something, right, yes, some probability. So the PageRank or whatever prestige of v is this probability times this one. Similarly, you have other types of nodes, okay, and you sum them up. This is time homogeneous. So how do you define this p of uv? As I mentioned, p of uv is basically can be in two ways. If the degree of u is greater than 0, and if the degree of u is equals to 0. If the degree of u is equals to 0 means it is a dead end, u does not have any outward edge, forward edge, then it would be 1 by n. If this is not a dead end, then a normal PageRank equation d into one by degree of u, right. So this would be multiplied with this one to get the PageRank, but this is just a transition probability p uv. There is no t factor here, remember this. So this is homogeneous, okay. So in case of DivRank, what we say is that, let us start with some initial transition probability p0 uv, and this is some kind of prior belief or prior reinforcement, whatever, right. And what is NTV? NTV is the number of visits of node v till time t, okay. And the idea is that the probability, this transition probability u comma v at time t, this would be proportional to p0 uv times NTV, meaning say this is u, this is a, b, c, right. In the PageRank, you can choose one of these nodes a, b, c uniformly and random and you jump, but in case of DivRank, it depends on the visiting probability in a, in b and in c. Say for example, this node has been visited multiple times, so it is highly likely that the random walker basically move from u to a, not to b, not to c, okay. And this is the idea. Think about it, what is happening here. So for a random walker, basically the random walker keeps on moving to such nodes which have been visited by the random walker in the past multiple times, okay. So in turn it basically absorbs on the prestige from its neighborhood nodes, its neighboring nodes, okay, because of this reinforcement, okay. So now let us look at the general form of DivRank. So PTUV, right. So initially we have this one for in case of PageRank. Now we define a time heterogeneous random walk PTUV. This would be some sort of 1 minus d plus d, okay. You have some prior about v, p star v, this is prior probability, prior of v. This can be 1 by n, if all the nodes are equally likely, right? But you already know, let's say you already know that this set of nodes are more likely to be visited, independent of their previous visits. You know that, okay, these nodes, these restaurants are owned by say Tata, or all these this business guy Oberoi or so on. So they would automatically attract audience. Okay, so therefore for those nodes you can give more prior, for other nodes you can give less prior. Okay, so this is same as this part. Now here is the tricks. So d times, now this is not uniform. Okay, now you replace this by this. So earlier this was 1 by degree. Now this is P0 UV times NTV summation of P0 UV NTV over all the V in the graph. Okay. So what it is saying? It basically says that the jump probability, the random jump, the jumping probability, this transition probability is proportional to this one. In other words, this is proportional to this one because this is fixed. This is fixed. You can fix it. Okay. And the denominator is basically useful because you wanted to make it as a probability. So denominator is basically same as, is basically sum of this quantity across all the nodes, so that this part would be a probability. Okay. This is your new transition probability. Now you can define P0, this P0 UV, right? I said this is constant, right? This is kind of a constant because this is not independent of time. It can be, I mean, you can use, I mean, you can basically incorporate the degree information here as well, because so far you have seen that degree information, degree of node U has not been considered anywhere, right? Here degree of U was considered, but here degree of U has not been considered. So you can consider P0 and you can add you can incorporate the degree information, degree of U in some ways. You can say that, okay, let's say if U not equals to V, okay, it is basically 1 by degree of U, right? If U equals to V, then you have some alpha, say this is 1 minus alpha. Okay, this can be a prior. Now if this is a prior, then the prior is same as the prior that you use in case of PageRank. Okay, so the main difference is this part, this component. Okay, so ultimately your final DivRank, right, is essentially what? Is essentially this one. So all the probabilities okay. So you at time t you look at the transition probability from U to V. So you want to you are computing the final DivRank value of node V. So you look at all the edges moving towards V, right? So P0 PT UV, all the UV edges, right? At time t, all the inward edges, right? At time t, and you multiply it with the prestige of U. That would give you the final ranking. Okay. Now this is the idea behind DivRank. So in other words, in short, if I explain this, it basically gives you a way to a node to compete with each other, to compete with its neighbors, right? And if you somehow are able to attract the random walk process or the random walk towards you again and again, or say if the museum somehow has been able to attract audience in the last few months or last few years, it is highly likely that in the next year it would again attract more audience. Same for students, right? And this and remember, this doesn't depend on who is pointing you. Of course, it is dependent on who is pointing you, but it also depends on your own capability. Say you are not that old restaurant, right? But you have created your restaurants with lots of passion, and you are pretty sure that it would immediately attract people, right? It doesn't need to wait for 1 month or 2 months or 1 year, right? That kind of flexibility is not provided in case of PageRank, but that is provided in case of DivRank. Okay. Now DivRank is not only used for web page ranking, it can also be used for graph summarization, graph summary generation. For example, in case of graph summary, what we are interested in, we are interested in returning nodes or subgraphs of a node, subgraph of a graph which are diverse but prestigious as well, right? So you want to choose those subgraphs or those nodes which are far apart from each other but prestigious. Okay, prestige is also important. So these two things are very nicely balanced in case of DivRank. So I stop here. In the next lecture, we will discuss other kind of metrics like seam rank, meta path and path seam, and so on and so forth. Okay, so we stop here. Thanks.